Hey everyone, today we're going to be talking about mirrors and lens. Before we get into it, we have to discuss a few important definitions and terms. The first thing we want to talk about is what a real image is, as well as what a virtual image is. Now, a real image is when light actually converges from the position of the image, while a virtual image is when light appears to converge from the position of the image. Now, I know that sounds a bit confusing, but don't worry, I'll explain and clarify it later. Now, another thing we need to talk about is something called the focal point, the focal length, the radius of curvature, and what all those terms mean. Now, when you have, let's say this is a mirror, obviously, when light, and this is assuming that the object is at infinity, so light is coming like this as a wave, it's going to reflect off the mirror. And once it reflects off the mirror, you notice that they're all converging at this one point. All converging at this one point. This point right here is the focal point. The focal point is the position where light waves converge and they almost like combine, they come together. The distance from the mirror or the lens to the focal point is called the focal length, and the distance from something called the center of curvature to the mirror or the lens is called the radius of curvature. Now, when you're talking about lenses and you're talking about mirrors, the radius of curvature just means you have to imagine a line. And the important thing about radius of curvature is that radius of curvature is it's double the length. It's 2 times the focal length. So focal length times 2, that gets you the radius of curvature, and that's the distance to the center of curvature. Another thing we need to talk about is what concave and convex means. What you need to know is concave means that it's curving inward, and a good way to think about it is like imagine here, the fact that it's going inward like this, rather than it going upward, like it's extending. It's almost like going inward. So the best way to think about that is it's kind of like the inside of a cave. Um, so that's what concave means. It's that it's curving inward. It goes into itself, and it's kind of like skinny. Convex means that it's curving outward, so it's protruding. So if you see here, it increases it increases near the middle, and then it decreases going to the ends. Another thing we need to talk about is something called DO and DI. DO basically means the distance from the object to the mirror, the lens, and DI means the distance from the image to the mirror and the lens. So if we look here, let's say that the object was here, for example. If this object was right here, let's say this is you, and then you end up making an image. So let me just erase some of that. The image would be around, let's say it would be somewhere here. And I'll explain why it's inverted and what that means, but assume that the image is here. To go the distance from the image right here to the mirror of the lens, that's the DI. To go from the object to the mirror of the lens, that's called DO. And then the height of the object, it's HO. That's the height of the object, and there's also the height of the image. This is HI, and then obviously HI here would be negative. We'll talk about that more later. Something else I need to explain to you is a great acronym that you should commit to memory, which is UVIR. And UVIR means that anytime you see an image that is upright, always know it's going to be virtual. And anytime you see an image that's inverted or real, know that the opposite is true, which means that If it's real, it's going to be inverted. If it's inverted, it's going to be real. So commit this acronym to memory, UVIR, because it's going to be very important when you think about convex and concave lenses and mirrors. Now, before we get into spherical mirrors and lens, we need to talk about plane mirrors. Plane mirrors are the mirrors that you see in your bathroom, where you see yourself. And a good way of applying what we've learned is to consider that the real image could be here. So let's say that you're looking, like let's say that you have a mirror right here, okay, and this is like kind of like the bathroom. This is like you can like wash your hands here, something like that. Um, if you're looking downward, um, you would see the virtual image of the real thing. So imagine this eye. It's looking at the real image. You think that it's looking at the real image, but it sees it on the opposite side of the mirror. And that means that it is the virtual image. And that's because mirrors are different than lens. What counts as a virtual image is different than for a lens. Because mirrors have their virtual images after them, while lenses are the opposite. And I'll explain that more later. So plane mirrors are flat reflective surfaces. They cause neither convergence nor divergence of reflected light waves. So light is just coming, it goes back the same way. It's coming that way, goes back the opposite way. An opposite to spherical mirrors and lens. Okay, now to talk about the idea of converging systems and diverging systems, they're going to be useful to categorize the different lenses and different mirrors. So when something is converging, this means that it can either be a concave mirror or it can be a concave lens. And when it's converging, that means that it has a positive focal point, and it means that it can either be real or inverted, or it can be virtual upright, depending on where the object is. And if it's like after the focal point, before the focal point, after the center of curvature, it all depends. Diverging systems, however, include convex mirrors and concave lens. And this means that it has a negative focal point. And the reason why it has a negative focal point is because it only, and this is very, very important to know, only has virtual and upright images. And the farther away the object, the smaller the image. The best way to understand this is to look at examples and websites. And I've linked a website in the description that goes over the distance between objects and how the image would change. And this includes converging and diverging mirrors and lenses. So for the mirror, the real side is on the front of the mirror, and the virtual image is on the back of the mirror. And a great example of this is when you look at this example. After the mirror, this counts as a virtual image. But before the mirror, the side where the object is, that's where the real image is. And the trick I'm going to teach you is when you have an object and it has a mirror and you're not sure if it's a real image or if it's a virtual image, if it's on the same side as the object, then know that it's a real image. If it's on the opposite side of a mirror, then know it's a virtual image. The opposite is true. If this was a lens, then the fact that it's on the other side would make it real. And it being on your side means it's virtual. So for a lens, real side is on the opposite side of the lens, and the virtual image is on the same side. Now, the best way to think about how these things work together is to look at a specific diagram. This is a ray diagram. It has the light waves and how they converge, and it shows you the way that the MCAT may ask a question or how you want to visualize things. So imagine here that you have parallel rays that are coming up to a concave mirror. And remember, a concave mirror is something that is converging. And we know that since it is cave, it means that it is always going to be curving inward. So, kind of like a cave. So it's kind of like this. And this is what they show us in the picture here. The distance from the mirror to the focal point is, as they said, the focal length and the radius of curvature, and this point, which is the center of curvature. Now, all the light rays are converging this one point, the focal point, and that is important to think about. Another thing is how it looks like for a convex mirror. A convex mirror has light waves that are parallel, and they're coming to the side, and rather than going inward, kind of like the concave mirror, they go outward. So they're not going inside. So if this was a concave mirror, it would go inward, kind of to the focal point, but it doesn't do that here because this is a convex mirror. What that means is that there is no focal point at your side. No focal point at your side. Rather, it is at the opposite side. And this is what I mean when I say it has a negative focal point. Because for mirrors, if the object or the image is on the same side, then it is positive. But if it's on the opposite side as the mirror, then that would make it negative. And lens, the opposite is also true. So, as I mentioned, f is equal to r over 2, which means the focal length is equal to the radius of curvature over 2. It's half. And this is a very important formula to know, which is 1 over f equal 1 over di plus 1 over do. I've seen this come up many times in many practice exams for the MCAT. And this is equal to 2 over r. Because you do some manipulation, you flip this, you get 1 over 4 is equal to 2 over r. And important things to know is you don't always have to draw a ray diagram to understand how the image is going to be. If the object's di is greater than do, the distance from the image to the mirror of the lens is greater than the distance from the object to the mirror of the lens, that means it's a real image. If it's less than do, then that means it's a virtual image. Another important formula to know is the magnification formula. And this is it's equal to negative di over do, and that's equal to the hi over ho. Now you might be wondering, there's negative at the di over do, but there's no negative at the hi over ho. This is because hi, if it was negative, then that would then its sign would be there. But di, even if it was on one side or if it was on the other side, it would always say positive because that's distance. But height is different. And when you use this formula, if you get m greater than 1, then that means that something is enlarged. Less than 1 means something is reduced. M is negative means you would follow IR, which means, inverted and real. If magnification is positive, then that would mean it's UV, which is upright and virtual. Now, let's look at a few examples of convex lens. Because remember, convex lens and concave mirrors, as I mentioned, they can have real and inverted images, or they can have upright and virtual. And there's something else, they could have no image. So if something is farther away than the focal point, it is even farther than 2f, which means it's the center of curvature, then what would end up happening is it would be on, and this is for the lens obviously, so if it's on the opposite side, then that means that this is a real image. Then you notice that it's smaller and it's real, but it's inverted. But something else, it's reduced. Look how smaller it is compared to the object. When and the way you can think about this is di is smaller than do. which means that when you're writing the formula, a smaller number on the numerator, a small number on the numerator, and a larger number on the denominator means it's going to get a smaller number, which means it is reduced, following this formula. If it's exactly at 2f, then that means it would be the same size. di and do would be the same, so magnification is equal to 1, and it would just be real and inverted. If it's somewhere between the center of curvature and the focal length, then it would be larger, because do would be smaller than di, and that would make the magnification greater than 1. If it is exactly at the focal point, then there will be no image. No image is created. If the object is after the focal point, then it's going to create a virtual image, which means for a lens, it's at the same side. If this was a mirror, then it would be a real image, but since this is a lens, this is a virtual image. So it's virtual, and remember, if it's always virtual, it's always upright, because UV. And lastly is that and after that, it's kind of the same thing. So that's what you kind of want to understand for convex lens. However, for concave lens, and this is also true for convex mirrors, they're somewhat similar. And they're always going to have a virtual upright image. Smaller, if I remember correctly, it depends, but they're always going to have a virtual upright image. Now, let's talk about a concave mirror. Remember, a concave mirror means that it is going to be going inward. Now, let's say that you have an object right here. This object that is right here, it can have a lot of light waves coming out of it. One goes through the focal point. That doesn't really matter that much. What matters is that you noticed that the image comes in this point right here. And it's smaller because this is after the center of curvature. If it's between the center of curvature and the focal point, then it would be bigger, but it would still be on the same side. At the focal point, if it's exactly at the center of curvature, then it would be real and inverted, but it would not be magnified or reduced. If it's at the focal point, it's no image, and if it's after that, then it's a virtual image. This is a virtual image. Why am I showing you this? I'm showing you this to see the similarity between a concave mirror and a convex lens. They both follow similar rules, albeit the only difference is that one is on the same side, the other one is on the opposite side. And you see how after it becomes magnified, and they shared very similar rules. And for a convex mirror, it follows the same idea as a concave lens, but rather than it being on the same side, it would be on the opposite side. It would be somewhere here. Sorry, it would be on the opposite side of the image if this was obviously a convex mirror. Now, the last thing I want to talk about is something called the power, and power basically means the refractive strength, and this is measured in diopters. Power is related to the focal length, and remember, focal length is in meters for this formula. So the longer the focal length, the weaker the power. And this is important because the MCAT loves to bring the ideas of myopia and hyperopia, and both of these conditions are nearsightedness and farsightedness. And they often talk about, okay, where is the image doing? Because your eye is a lens, and it basically converges light at a specific point, and your brain basically visualizes that, processes that. So when you see myopia, always think about this, which is NMD FHC. So need medical doctors for helping children. Myopia always means that they have nearsightedness and they need a diverging lens to fix the problem. Because you remember, a diverging lens is gonna make them spread out more. So if I had a diverging lens, they would get farther away from each other, farther away. And this is what you need, because your nearsightedness, your lens is too strong, and it's converging the light waves too early. If it's hyperopia, then you have farsightedness, and the image is forming outside of your retina, so you're not able to process the image. In that way, you need a converging one. You need them to become closer. You need the lens, so once it passes the lens, they get closer and they end up converging. And that's how you get the idea of NMD. FHC, need medical doctors for helping children. It's a great acronym, and it should help you. Another thing is, when lenses are in contact and they're negligible distance, you would just add up the focal length and the power. You'd also add them up. For lenses that are not in contact, the image of one lens will become the object of another lens. So the magnification would just be magnification of the first mirror of the lens times the other one times the other one times the other one. I hope this video has helped you. And if you have any questions, please write them down in the comments, and I'll try to get back to you as soon as possible. Thank you.